This lecture slide deck is going to start us off with game theory. We're going to be covering the fundamentals. We'll look at sort of the basis of what a game is, normal form games, decision trees, simultaneous games, sequential games, repeated games, both um, infinitely repeated and limited repetition, and then finally strategies that players can adopt in games and how the players can actually change the game so that they increase the likelihood of cooperation. All right, so there's a lot we're going to cover here to sort of give you a broad idea of what game theory entails. Okay. So starting off, game theory fundamentally, as we discussed with chapter 11, is looked at strategic interactions among two or more people, right? So it's not necessarily useful for situations where someone is operating as if they are the only person in the environment. Often in markets, right, people go into markets, they don't consider how their purchasing of a sandwich is going to affect the price of that sandwich, right? Or if you purchase the newest video game console, you're not considering how you're going to affect the price of that console, right? So we would not use game theory for those types of decisions. What we would use game theory for is when someone is considering how they're wanting to respond maybe to someone else, or if they are considering how their choice will impact someone else. So as long as there's sort of consideration in another person in their decision, that's when game theory is useful. Okay. And it's not necessarily for I care about my mom, and so I'm going to use game theory to represent that. It's sort of when my choice depends on someone else's choice, right? So if I'm, um, for example, wanting to meet up with a friend, but their phone died, right? I'm going to think about if we're both on campus, okay, where on campus would they go? And I'm going to try to make a choice that aligns with what I think their choice would be so we can meet in the same place, right? That's when game theory is useful, when the choice of someone else is going to impact the choice that our individual of analysis is going to make. Okay. All right. So that's how we define then strategic decisions, right? It's just that the action is based on anticipation of what someone else is going to do. And we can apply this broadly, right? Game theory is not unique to economics, but economists do use game theory quite a bit. Some fundamental assumptions we're using here. These can be a little tough for folks because they're not necessarily always realistic. But first is that each player is self-interested. So that's that usual rational assumption that we make for economics. We're assuming that players are pursuing their own best interest, right? Second, information is symmetrical. And with this, that means that everyone playing the game has the same exact information. And usually that means that they have complete information. So when we get into the games, that'll mean that they know their payoffs and they know their opponent's payoffs as well. So they'll be able to reliably predict or anticipate, in most cases, what their opponent is going to do. And then our last assumption here is that the rules of the game are going to determine the game's outcome. Okay. And the reason for this is the rules of the game are going to shape the payoffs that our players face. And so if the rules change, the payoffs change, and so the player's behavior changes. Right. So what is a game? The most simple game is going to have two players, two decision makers who make a choice in response to payoffs, right? They each make their own choice. The choice that a player takes, or we call it an action that they take, is called a strategy. And then the payoffs are the benefits or costs that a player receives from an action, right? And thus the outcome of a game. And then most games we're going to see will have a single equilibrium where play settles, but that's not always true. There can be sometimes games with no equilibrium, or as we'll see, games with a mixed equilibrium. So there are several categories of games. First, we'll consider simultaneous games. These are what we saw with the Cournot and Bertrand models that we covered in chapter 11. Here, Yeah, participants are choosing their actions at the same time without necessarily knowing what their opponent is going to choose, right? Because the choice happens simultaneously. They will, however, know the payoffs that their opponent faces, so they can reliably often predict what their opponent will select. Repeated games are when we have simultaneous games happening again and again and again. So the classroom setting is a repeated game, right? We've interacted again and again and again throughout the semester, and that's affected your behavior in the classroom and it's affected my behavior in the classroom, right? If we were only meeting once, it's a guest lecture that only is going to happen one time that semester and likely never again. That's going to change how both of us interact with each other. Functioning cartels or collusions can be modeled as repeated games because those firms are continuously interacting with each other around this choice of how to restrict their output. Sequential games are games in which players take turns making decisions. So in these games, there's usually someone who moves first and then someone who moves second. So chess is a sequential game. Checkers is a sequential game. Um, we didn't get to this semester, but the Stackelberg model is also a sequential game. In that model, we take the Cournot model and we just have one for move first, right? Within games, there are different types of strategies that players will adopt. So, in order for us to predict the outcome of the game, we have to identify the optimal strategy that each player is going to take if we can, right? We can't always identify what that optimal strategy is. In those cases, there's usually no Nash equilibrium, which we'll get to in a second. But the optimal strategy is always going to be the action that results in the highest payoff. And usually it's one for one with the dominant strategy, but not always. So the dominant strategy is a winning strategy for a player regardless of what their opponent does. So it's what they will play every single time, and it doesn't even matter. They don't even need to consider necessarily what their opponent chooses. And so once we identify what a player's dominant strategy is, that is the one we know they are always going to reliably choose. And of course, if there is a dominant strategy, that implies that there's a dominated strategy. So that strategy is just the one that is um, never going to be chosen for a player. It's a losing strategy. It's going to make them worse off if they choose it, regardless of what their opponent does. And so they are never going to select a dominated strategy when there is a dominant strategy. Um, Given a dominated strategy, that does not necessarily always mean there is a dominant strategy, but when there is a dominant strategy, there is a dominated one. Okay. Now we're getting to how we represent games. So this is what we'll see first, and then later on in the slide deck, we'll see a decision tree, but this is what we call the normal form of a game. All right, this is what you saw in the chapter 11 lecture videos as well. We have two players, Warner Brothers and Disney, right? Each facing two actions, advertise or don't advertise, and then each facing a set of payoffs. Okay. Within game theory, there is a convention where player one is always on the left-hand side. So Warner Brothers here is player one. Player two is always on the top. So Disney is player two. And then when we look at the payoffs, player one's payoffs are always on the left, and player two's payoffs are always on the right. And this is going to apply to decision trees as well. Player one's payoffs are always on the left, and player two's payoffs are always on the right. Okay. So as we look at this normal form game, we're going to be able to evaluate it to identify the strategy that each player will take. Okay. So let's go through that together. So we want to find what is the dominant strategy for each production company. You saw this game already in chapter 11. We're just going through it again. All right. So what we're going to do is we'll start with Warner Brothers and consider the universe in which Disney advertises. Okay. So when Disney advertises, Warner Brothers wants to also advertise because their payoff is 250 million rather than a loss of 80 million. When Disney doesn't advertise, then Warner Brothers wants again to advertise because now their payoff is 550 million rather than 320. So we're going to see for Warner Brothers, their dominant strategy is advertise. Okay. And we know they will never, ever not advertise in this game. Now let's turn to Disney. So we know that Warner Brothers is going to advertise no matter what. So for Disney, we want to see what is their dominant strategy. If they don't advertise, they're going to lose 80 million. But if they do advertise, they gain 250. So that means that Disney too has a dominant strategy of advertising. And so the Nash equilibrium, which again we're going to get to in just a second, is that advertise, advertise, sell, right? That is where the game settles. Okay. All right. So here we'll stop, and then the next video will pick up talking about what is a Nash equilibrium.